Today is the last chapter or last part of the surface water, and also this is the last chapter for the hydrologic events. Then we are gonna go through the unit hydrograph, the statistical part of the hydrology. Today we are gonna calculate how we calculate the depth and velocity of the surface water. Let's jump to the next slide and then we will continue. The first subsection is flow depth and velocity. The flow of water over a watershed begins when water becomes ponded on the surface at sufficient depth to overcome surface retention forces and begins to flow. So it's overcome the friction and it starts to flow on the surface. There are two basic flow types. The one is, as you see on the top right side, overland flow, and the second one is the channel flow, as you see in the right bottom side. It's also called open channel flow. So overland flow, a thin layer of water flowing over a wide surface. As you see, there is a ponding and it flows due to the gravity. And channel flow is a much narrower stream of water flowing in a confined path. Basically, it is like a concrete channel. So we are like making like a confined or combine all the water in the branches into this channel, and then it starts to flow again due to the gravity. So let's go through the first part, is overland flow. Overland flow is a very thin sheet flow which occurs at the upper end of slopes before the flow concentrates into recognizable channels. So as you see in the representation of like a drawing, we have a slope, then the water as on the right side of this inclined surface is accumulated, and the depth is varying by the length. Okay, so we are gonna right now solve and we are gonna use continuity and momentum equation, and then we are gonna derive how we can calculate the velocity and depth of this overland flow. Okay, let's go through the continuity equation. We know that the working fluid is water. So when it's water, we know that rho is constant, which is density is constant, right? When it's constant, we can take it outside, so we can simplify our continuity equation as double integral control surface VdA, the velocity multiplied by the infinitesimal area, is equal to 0, which is input minus output, or input is equal to output, right? Or as we said, input minus output is equal to 0. So what we are gonna have is input our intensity, right? Intensity of rainfall intensity. So it's this guy, which is L0, this guy multiplied by cosine theta is gonna give us here this length, right? This L length is our cross-sectional area, which is L0 cosine theta is gonna give us this I L0 cosine theta is gonna give us our input. Output is infiltration into the soil, right? Infiltration into the soil again in the cross-sectional area. So we are gonna say F. So F L0 cosine theta plus the overland flow, which is Y multiply V multiply Y. So F L0 cosine theta plus Vy minus IL0 cosine theta is gonna give us 0, which is continuity equation. When we simplify again, we are gonna have the flow rate is Q0 is V multiply YY is equal to, either we can say V multiply YY is Q0, right? So it's the flow rate per unit area, which is again V multiply YY is equal to I minus F L0 cosine theta. This is our continuity equation. Okay, the second thing is momentum equation. In momentum equation, we are going to consider first laminar flow, but the uniform. So it's like wherever the length is, as we see from the beginning of this class, when uniform is everywhere is the same, right? Either like the depth is gonna increase uniformly. For this uniform laminar flow, we have a formula of the velocity is equal to the gravity multiplied by the inclination or the angle, the depth square over 3 kinematic viscosity. And as we see from here, this one is S0, but we can calculate it as SF, which is the depth on here over the length L. HF over L is gonna give us the same theta, okay, the S0. So when we go back here, we can consider S0 is HF over L, which is when we plug here, solve for HF, which is the depth of this water is 24, the kinematic viscosity, the length of the channel, velocity square over velocity, y 4y 2g. Why we consider this one? Because there is like the Reynolds number and blah blah, this dimensionless numbers we can consider. So we can change it to Darcy-Weisbach equation. That's why we divide it into this form. Here the F is 24, the kinematic viscosity, the velocity multiplied by y, and L over 4R, y is equal to, we say, the hydraulic radius is equal to depth, and v square over 2g. Okay, the F we can consider as 96 over Reynolds number, which is Reynolds number is 4 VR over kinematic viscosity. When you plug here, you will see it's gonna be 96 over Reynolds number for laminar flow again. We need to take into account that the flow remains laminar if Reynolds number smaller than 2000. We know that if it is from 2000 to 4000 is a transitional flow or regime, and above 4000 we consider as turbulent flow for the channel. Here we all see these guys, we remember from the hydraulic class, so we are going through again the same thing. This is just basic knowledge, so I'm not gonna go detail. I'm just we just need to concentrate like where it's coming from. Okay, For laminar sheet flow under rainfall, so here there is a rainfall going inside the play role in the consideration. Before it was just like the rain occurred and then there is a ponding and its flow starts. Here there is flow and rainfall again. Like by the way, the fluid is flowing, the rain is coming into play. So when it's this one, F is the form of CL over Reynolds number, where CL is resistance coefficient and calculated as this is the empirical formula from experiments. CL is equal to 96.108, the intensity of rainfall power 0.4. So it increases the F, okay, friction factor. I is the rainfall intensity in inches per hour. We need to take it into account, okay, so it's inches per hour. When we solve for y is equal to F V square over 8G at 0, which is, we can make it with the Q0, which is the flow rate per unit area, F Q0 square 8G S0 power of 1 over third is gonna be our formula for uniform laminar flow. Okay, let's solve one example. So in order to understand better, a rainfall of intensity 1 inch per hour falls on a uniform, smooth, impervious plain 100 feet long at 5% slope. So L is equal to 100 feet and S0 is 5%. Calculate the discharge per unit width, the depth, and the velocity at lower end of the plane. We need to take the kinematic viscosity of 1.2 multiplied by 10 to the power minus 5 feet square over second. Let's go to solution. Okay, in order to calculate the discharge per unit width, we know that we have a formula of Q0 I minus F L0 cosine theta. So we know that the F, the infiltration rate, is 0 due to impervious field or the territory, and I is 1 inch per hour, L0 is 100 feet long. We need to convert it to like this, inch to first of all feet per second, then after that we need to multiply, then cosine theta. We are gonna calculate this theta from the slope. Okay, let's start. First of all, let's change it, this 1 inch per hour to feet per second, right? Because we need to multiply by feet, then our Q0 is gonna be feet square over second. So 1 inch per hour is 2.32 multiplied by 10 to minus 5 feet per second. Okay, we converted this one as inch per hour to feet per second. Good. So we are gonna calculate theta. Theta is arc tangent, which is tangent minus 1 of S0, which is our slope. Our slope is 5%, which is 0.05. So tangent minus 1 of 0.05. So when we calculate this guy, and theta is gonna be equal to 2.86 degree. So we just need to plug cosine theta here. So let's calculate also cosine theta, which is cosine 2.86. When you multiply, is gonna be 0.999. So everything is ready. So we can calculate it. Q0 is equal to 1 inch per hour, which is 2.32. 2.32 multiplied by 10 to minus 5 minus infiltration rate, which is 0 because it's impervious. The length is 100 feet. Just multiply 100, and then what we need to multiply cosine theta, which is 0.999. Okay, when we multiply each other, we are gonna have 2.31 multiplied by 10 to minus 3, which is feet square over second, is our Q0. So we calculated first the discharge per unit length. Right now, the depth and velocity, we need to multiply it. We need to find it. Okay. So in order to find the depth, let's go again. So in order to find the depth, we have a formula of parenthesis of the F, which is this F is friction factor Q0 square over 8 gravity and the slope and power of all of them 1 over 3. Okay, so what we don't know, Q0 we already calculated, 8G is known, S0 is known, only F is we don't know. How we are gonna calculate F if there is rainfall? We know that is gonna be CL, the resistance coefficient, over Reynolds number. From our knowledge, CL is equal to 96 plus 108 I power 0.4. But we know that we need to use I as inch per hour, so we don't convert it. So 96 plus 108 1 power 0.4, which is CL is 204. Okay, we already found CL, but we don't know Reynolds number, so we need to calculate right now Reynolds number. How we are gonna calculate Reynolds number right now? So Reynolds number is for velocity, the depth over the kinematic viscosity, right? But we don't know why. We don't know why. We want to calculate y. So instead of Vy, we can use for Q0, which is discharge per unit width, over kinematic viscosity, right? Okay. So it is 4 multiplied by 2.31 times 10 to minus 3 over kinematic viscosity, which is 1.2 multiplied by 10 to minus 5. When we substitute these guys, when we calculate, 770 is our Reynolds number. Okay, let's go back in this formula, and we can use this formula to calculate y right now, because we know that we can calculate f right now. What is f? F was CL over Reynolds number, which is 0. So it's gonna be how much the CL? 204 over 204 over 770, which is 0.265. Okay. When we substitute it in y, this formula is 0.265 multiplied by 2.31 10 to minus 3 square over 832.2, which is G, and 0.05 is the slope, and power of 1 over 3 is given us. The depth is 0.0048 feet, which is 0.06 inch. Okay, let's calculate the velocity. The velocity is, we know that just before v multiplied by y is q0, so q0 over y, which is both of them right now known, can be calculated the velocity. So like this, we know that q0 is 2.31 multiplied by 10 to minus 3, and y we just calculated. This is feet square per second, don't forget. So it's gonna be 0.0048 feet of y, and when we divide each other, we are gonna find 0.48 feet per second is the velocity of this hydrologic event. Okay, we calculated everything here, so we finish up the question. So in field and unevenness topography, we need to use y is equal to alpha q0m. For laminar flow, what is like previous we defined is m is over 2 over 3, and alpha is f over 8g s0 power 1 over 3. As when you substitute this one, you will see the previous equation is applied here. When the flow becomes turbulent, Manning's equation plays role, and which is here the Manning's equation, which is velocity is equal to 1.49 over n, the hydraulic radius power of 2 over 3, and the inclined surface slope 1 over 2, like square root of the slope. So when you plug this equation and then you solve for y is equal to n q0 over 1.49 s0 1 over 2 power 3 over 5, which alpha here n over 1.49 S0 1.1 over 2 and close parenthesis 3 over power 3 over 5 and m is 3 over 5. For SI unit, this is British unit. For SI unit, you need to change alpha as n power 0.6 over S0 power 0.3. This is for the turbulent flow if we want to find the depth of this overland flow. Let's go through the example and then we are gonna solve and we can understand better. Okay, in this question, calculate the depth and velocity of a discharge of 2.31 multiplied by 10 to power 3 cubic feet second per feet, which is width, on turf having Darcy-Weisbach F is equal to 75 and a slope of 5%. Again, we are going to take the kinematic viscosity of water 1.2 multiplied by 10 to minus 5 feet square over second. Okay, in this question, first of all, we need to check if this flow is laminar or not. So Reynolds number, as you remember, is 4Q0 over kinematic viscosity. So 4 multiplied by 2.31 multiply 10 to the power minus 3 over 1.3 multiplied by 10 to minus 5 is giving us the Reynolds number as the previous example 770, which is below 2000, below n equal to 2000, so laminar. So check, right? Okay, we know that we need to calculate alpha, because let's again write it down, our formula, the depth is equal to alpha multiplied by Q0 m. For laminar flow, we know that m is 2 over 3 and alpha is equal to F over 8 G S0 and power 1 over 3. Right? It was just given from the equation. So the question says the Darcy-Weisbach friction factor is 75. Just plug here. We know that 8 and G is 32.2. 32.2. Let's make it in parentheses, 32.2. And S0, which is our slope, is 5%, so it's gonna be 0.05. So we can calculate it alpha. Let's see here. Hold on. Oh, this is. Let's write it down. Close the parentheses of 1 over 3, which is equal to 1.8. 1.8 is our alpha. So if I know alpha and I know that the discharge coefficient, so y is equal to 1.8 multiplied by 2.31 times 10 to minus 3, right? 10 to minus 3, 2 over 3. So it's gonna be 0.031 feet depth of water on turf. So in order to calculate the velocity velocity was Q0 over Y, which is Q0 again 2.31 multiplied by 10 to minus 3 over Y is 0.031. So it means that velocity is equal to 0.075 feet per second. 0.075 feet per second on turf field or basement. The water has the, like, when there's like this kind of discharge, like 2.31 multiplied by 10 to minus 3 cubic feet second per feet. If we have this much discharge, over length discharge, we will have depth of 0.031 or 0.4 inch. Let's write here also 0.4 inch. 0.4 inch, or the velocity of 0.075 feet per second. In this example, we need to calculate the discharge per unit width, depth, and velocity at the end of a 200 feet strip of asphalt of slope 0.02, which is 2%, subject to rainfall of 10 inch per hour, with Manning's N is equal to 0.015, and kinematic viscosity is again 1.2 multiplied by 10 to the power minus 5 feet square over second. Okay, in this question, again, we need to calculate the Q0, which is Q0 is equal to I minus infiltration rate, the rainfall intensity minus infiltration rate, L0 cosinus theta. Same thing we need to apply. It's an asphalt, so impervious, F is goes to 0. So we need to calculate the theta. Theta is tangent minus 1, 0.02, which is 1.15 degree. So when we multiply cosine theta, cosine 1.15 degree is almost 1. So it's negligible. So it's almost horizontal, right? So Q0 is gonna be our I. So first of all, let's convert this I is equal to 10 inch per hour to feet per second, which is this time 2.32 multiplied by 10 to minus 4 feet per second. So Q0 is equal to 2.32 multiplied by 10 to minus 4 multiplied by minus 0, then L0, which is 200 feet. Wait, we need to multiply by cosine theta, which is 1. Okay, so Q0 is 0.0464 cubic feet second over feet. So we already find for, in this case, the discharge per unit width. So right now let's go through to the depth of this flow. First of all, let's check if it is laminar or turbulent. So we need to calculate the Reynolds number for Q0 over the kinematic viscosity for multiply by, this is our Q0 is 0.0464 over kinematic viscosity is 1.2 and 2 minus 5, right? I am not doing wrong. Okay, so the Reynolds number is 15,333, which is turbulent, right? This is bigger than 2,000 or like 4,000, let's say. It's turbulent, like transition. Let's take it that now count like a turbulent, like it's already 4,000, bigger than 4,000, let's say. It's just fully turbulent. Okay, if it is turbulent, we are gonna use again this y is equal to alpha Q0m, which is m here is 0.6, so 3 over 5, right? 0.6. So alpha, how we are gonna calculate alpha if we have the turbulent flow, n over 1.49 S0 1 over 2 power 3.5. So let's add it up everything in order to calculate this here. Okay, the roughness is n is Manning coefficient 0.015 over 1.49. Let's put in the parentheses and multiply by S0, which is the 0.02. The slope is 0.02, 1 over 2 square root, right? And this power 0.6, 3.5, 3 over 5, 0.6. So this guy is gonna be 0.205. Like when we calculate it, alpha is 0.205. Can find it. Okay, so let's do here y is equal to alpha Q0m. Like we know that this one, so alpha is 0.205 multiplied by Q0 is 0.0464, 0.6, and y is equal to 0.032 feet. So we found it for this case the depth of the overland flow, velocity as we used to Q0 over y, which is Q0 is 0.0464 over y is 0.032. So the velocity is 1.43 feet over second. So the velocity is high, as you see, and we found that the discharge per unit width, the depth, and velocity. Question is finished up here. Okay, the next subsection is channel flow, which is we need to consider a channel of length LC, which is here, as you see, LC from this side to the end, and that is fed by overland flow from a plane as shown in the figure. So this is the overland flow is filling this channel, is feeding this channel. Okay. The overland discharge is Q0, as we see here is Q0 feeding this channel. So the discharge of the channel is the capital Q is Q0 plus LC. We know that this is the flow rate multiplied per unit width. So Q0 LC is gonna give us the flow rate of this channel. To find the depth and velocity in the channel, an iterative procedure of Manning's equation is applied. This is the Manning's equation. Okay, Q is equal to 1.49 over n, S0 1 over 2, the area and hydraulic radius of over 2 over 3. This is our Manning's equation. We need to apply here. Then we are gonna find the depth and the velocity of the this flow. So we will see the next chapter, the next slides, how we are gonna solve this iterative procedure. The one that we utilize for solution of Manning's equation is Newton's method, Newton's iteration. There is no general analytical solution to Manning's equation for determining the flow depth given the flow rate. Therefore, Newton's method can be applied to have a numerical solution. In this process, which is like the Newton's process, approximate Qj is compared with the actual flow rate, which is Q. We are going to compare, so we are going to find the error to obtain Y, okay, or to obtain the approximate solution, the best approximate solution for the depth of this flow. In order to use Newton's equation, we need to take the derivative or gradient of f with respect to y. So df over dy is dqj minus dyj, because q, which is actual value of this flow rate, is constant. So when you take the derivative with respect to y, this guy is gonna go to 0, and so let me show you previous slide. This one, df over dy, q dqj over dy, this q goes to 0. So we have the final version of this equation. So df dy, which is this one, so we are gonna put qj in the Manning's equation, and we are gonna take the first derivative with respect to y. So you need to do like, let's put prime here, which is wrong here. So we need to take this one, d over dy derivative. When we take the derivative, it's gonna be qj, again this by itself, and 2 over 3r dr dy plus 1 over a dA dy. Interesting readers can take this derivative, and they will see you guys are obtain this equation. Okay, now we can use Newton's iteration. From the literature, we can see Newton's approach is, if we want to find yj plus 1, which is the one step ahead of y is equal to previous step minus the function, which is whatever function with respect to yj, over the derivative of this f with respect to y. Okay, so when we plug instead of f our what was it, qj minus q, right? When we plug instead of this guy qj minus q, we will obtain this equation. Okay, after the manipulation, and then when we substitute the derivative and fyj, we will have this equation. After that, we substitute the necessary derived equation and manipulate it. It yields to, for rectangular channels, in this form. Okay, it's gonna be yj plus 1, yj minus 1 minus q over qj over 5bw plus 6yj over 3yj in the parentheses of bw plus 2yj, where bw is the channel width. Okay, this is for only rectangular channels. So for any other geometry, it changed this equation. This here is changing for another equation. We need to substitute. Let's see the table and let's observe how it changes. Okay, here the rectangular, trapezoid, triangle and circle kind of channels, and how we can calculate the area, wetting perimeter, hydraulic radius, top width of, and the width, which is b, or what you call top width, and the whatever we needed for the previous equation. Let's go. It's here. Okay, from the Newton's iteration we obtained. So rectangular channel, we use this guy as previous example. Let's go again. As it's here, we use this guy. But for trapezoid, we just need to substitute this guy. For triangle, we just need to substitute this guy. And for circle, we just need to substitute this guy. Right? So take it back. Let's take this one. Okay. So if we change the channel width, we need to change whatever you use, and we need to apply it. Okay, let's solve one example. We need to calculate the flow depth in a 2-foot wide rectangular channel having the roughness of 0.015. The slope is 0.025 and the flow rate is 9.26 cubic feet second is our question. In this question, we need to calculate the flow depth for the 2-foot wide rectangular channel. First of all, we need to use the Manning equation in order to find the flow depth, the flow rate. So this guy is the Manning equation, as you guys remember. We use here the rectangular channel, right? So let's go back to our table. Let's see here. Let's go back to table. As you see, for the rectangular side, we have the hydraulic radius, which is r, is bwy, bw2y, and the area is bwy multiplied by y, which is our for rectangular shaped geometry for channel elements, right? So okay, let's just for area, let me put this guy here. Here, let's put here. This is for area. I need to plug, and which one is it? The other one is hydraulic radius. Okay, if I plug here the hydraulic radius, then I need to calculate the Manning equation. So if I plug this guy, so Q is gonna be 1.49 over N. S0 is gonna be constant, 1 over 2. So as you see, BWY, but A is gonna be constant, and then R is gonna be coming 2.2 over 3. So it's gonna be BWY power of 5 over 3 over BW plus 2y. This is 2 over 3. It's gonna be our Q flow rate. So let's calculate it. 1.49 over N, which is N is 0.015 multiplied by S0 1 over 2, which is 0.025 square root of this guy, right? Then we are gonna calculate this guy, which is BW is 2 because 2 feet wide, as it's in here, and the depth we don't know. So Y, let's say J, we don't know, 5 over 3 over, this is 2 plus 2yj, this is 2 over 3. So this is equal to qj. What does it mean? It means, let's make it more simplified. Then after that we need to make it iteration procedure. So it is gonna be 31.41 yj 5 over 3 over 1 plus yj parenthesis over 3. So we are gonna find it this one as an iterative procedure. Let's go a little bit here because we need to find also the another term which you remember, 2dr over 3r, sorry, 2 over 3r dr dy plus 1 over a dA dy, which is rectangular portion from the table. It already derived, so it is 5 bw, right, plus 6 yj over 3 yj multiplied by bw plus 2 yj. It's already given in the table. This is equal to, let's say, and this is equal to, instead of bw we need to put 2, so it's 10 plus 6 yj and 3 yj multiplied by 2 plus 2yj. So when we manipulate, it's gonna be 1.667 plus yj over yj over 1 plus yj. So what do we need to do? We need to use the Newton's procedure, right? Which was, let me write it here, yj plus 1 is equal to yj minus q over qj and blah blah, right? So I will just plug it down the numbers, which is wait up yj 1 minus q over qj over 5 pw plus 6yj, which just we derive over 3yj over bw plus 2yj, right? It was these guys. So what we need to do, we just need to plug this equation in order to find our iterative equation. So it's gonna be yj plus 1 is equal to yj minus 1 minus 9.26 over qj. So is yj 1 plus yj over 1.667 plus yj. So in here we need to make an trial and the iterative procedure in order to find the solution. Here we just need to plug one number to yj. Like if you plug yj 1 feet, and when we plug here, we are gonna have the qj from, as you see, q is here. We need to plug yj here. Then q, we will have q as 19.79. Is that close to our actual value? No, our actual value is 9.26. Then we will continue. Let's continue. Let's plug this y1 and 19.79 into this one. So in order to find the next yj plus 1, so it's gonna be again yj, the next step is gonna be 0.601. Then when we plug qj, is gonna be 9.82. It's still not enough, so we just plug these two numbers here in order to find our next y value, and the next y value is 0.577. Then when we plug here, then our qj value is gonna be 9.26. So we will say, okay, this is same as our actual value, and we just keep it this one here. We will say, okay, this, in order to make it like a correct one, if you want, you can just 9.26, then plug here, then you will see, you will find again 0.577 here. Then this value and this value, when it is same, we will stop our iteration, and then we are going to say, okay, we have it. our solution. So this question is done here. And the last example is compute the velocity and depth of flow of 200 foot increments along a 1000 foot long rectangular channel having width 2 feet, roughness n is equal to 0.015 and slope s is equal to 0.025 applied by a lateral flow of 0.00926 cubic feet second per feet. Okay, now in this question we are gonna use an increment procedure. So let's make a table. So distance, let's say we have distance like or L. Okay, so it's gonna start from the 0.200, 400, 600, 800, and then it's gonna go to 1000. Let's say one. Let's put here. So we are gonna find the flow rate, the depth of the velocity, and then depth of flow, and then velocity. So for each case, when it's 0, Q is 0, the depth is 0, velocity is 0. When it's 200, Q says is supplied a lateral flow of 0.00926 cubic feet second per feet. So we need to multiply by 200 feet of this guy. So it's gonna be 1.85 for this guy. And when you multiply by 400, it's gonna be 3.7. When you multiply by 600, 5.56. And let's go through the here 800. When it's 800, it's gonna be 7.41, and let's go here 1000. When it's 1000, is 9.26. 9.26. Okay. So as you apply, in order to find y, we need to apply again the same equation as, let me show you that, guys, previous example, which is, let me plug here, as here, okay, for rectangular channel and for 0.015 roughness and 0.025 slope and the width of 2. This was our previous example iterative procedure. So what we need to do, we need to apply y, like we will start at let's say 0.1, then we are gonna calculate qj, as we know that our qj was calculated in this form. Let me show you guys. Right, we have the qj in this form, which is bw is 2. Just plug 2 here, and then we will calculate qj by applying 0.1. Then we will see if q is approach 1.85, what is our y. And when you do this one, you will see that at 200 is gonna be 0.2 is our the depth of this flow rate, 1.85. Velocity, we know that velocity, how we are gonna calculate, is q over this q over area. Area for the rectangular channel is bw over y, which is bwy, which is 2y. So q over 2y, we know that y is here, so 1.85 over 0.4 is gonna give us 4.63 feet per second. Same thing is here, so I'm gonna just write it down the answer. 0.31 for 400, then 5.97 for this corresponding velocity, then 0.41 for 600 distance from the end, so it's gonna be 6.86. Let's go through the other one, and 0.49 after 800, so it's correspond to 7.56 feet per second velocity, and in 1000 distance is 0.58 depth of water, and its velocity is 8.02 feet per second. So this is how we solve this kind of incremental questions, okay, with tabulated form, with using by using the Newton's iteration. It's the same thing basically, just like incremental procedure plays into role. That's it. Here we are. We finish up surface water. We are done here. Next chapter is gonna be unit hydrograph. We are gonna go through a little bit statistic right now. You guys have 3 questions for the homework. The first one is compute the uniform flow depth in a trapezoid tunnel, having the roughness, the slope, and flow rate, and everything is given. So you guys can do this question. Then you will have the second question. You need to calculate the discharge per unit width, depth, and velocity for rainfall of 3 inch per hour falls on a uniform smooth impervious plain that is 50 feet long. Then you need to take the kinematic viscosity 1.2 multiplied by 10 to minus 5, and roughness is 0.015. Then after that you need to do the same question for if the rain falls on a grass with an infiltration rate of 0.5 inch hour, and that's a Weisbach roughness. F is 100. So I will expect you to submit this homework next week.